Budapest University of Technology and the Hundred Institute. He's going to talk about Brownian web distance and Bernoulli-Exponential first passage percolation. Balint.
Thank you very much for the introduction and for having me. Let me start. Oops, I have to switch on microphone. Okay, I hope that everybody can hear. So the introduction, I will start with telling you what is this talk about. Actually, I will talk about two models, mainly as you see in the title, the Brownian web distance, and also a version of this model, which is the Bernoulli-Exponential first passage percolation. The Bernoulli web distance actually counts. Sorry, just double checking your microphone. Yeah, at the beginning I haven't switched it on, but now it's okay. You're good. So there is a discrete object, the random walk web distance, which I define first, and then its continuous version and the scaling limit is going to be the Brownian web distance. I will define all these things in detail, so you will see what they are. And the main results about these models is the convergence, and also that despite the fact that this Brownian web distance will turn out to be a scaling limit, it still shows KBC fluctuations. We'll see in detail. So these are the main result of the Brownian web distance. Then I introduced a second version of the model, which is the Bernoulli-Exponential last passage percolation, and in the end, I will show some ideas if I have time. And so this is all, or partially, this is joint work with Balint. And let's see some motivations. The KPC universality class is motivated by different physical phenomena. Maybe most of you know it very well, that if we are dealing with some surface growth or boundary evolution effect in physics, and then the fluctuations are usually described by the KPC equation. KPC equation, you can see down there, which was defined by Carter, Parisi, and Zhang. Therefore, it is called KPC equation, back like almost 40 years ago, which is a stochastic partial differential equation, which is also non-linear. And notice that its psi is here a two-dimensional line noise. Okay, so what is it? So we can think about this H as being a function of space and time. So it tells us that at time t, how does this surface look like? And this is just a snapshot of some simulation. So as I said, the KPC equation was believed to describe a lot of physical phenomena, but also there are some mathematical models in which we observe fluctuations that have a universal behavior, namely that independent of the small details of the model, we will see the same scaling exponents and the same scaling relation. What are these scaling exponents? This is the famous 1, 2, 3 scaling. If you look at the red numbers here, then you see that these are the 1, 2, 3. So you think about the rescaled height function, you subtract the mean and divide by n to the 1/3. Then you believe that, or partially prove that this converges to a universal object. There are various levels of understanding of this. If you just want, so the easiest one is that you fix t and x also, then this is just a single random variable. It is converging to, depending on the initial condition, maybe the trace rhythm distribution. But also if if you make it dependent on t and x, then you can have joint distribution. And also recent development is that there is the directed landscape which describes the scaling limit of such height differences.
So that's not exactly correct. So it's not the height difference. What you do is you start the k+e point at a narrow edge at xt.
Okay.
With the same noise as you start for every xt, and then you look at the height at ys. So if you want to write, which is a different story.
Okay.
Connection.
Okay, but
yeah, this one what you're saying is not correct. But it's okay. It's close.
Okay.
Sorry. It's morally correct.
Okay, so what you say is that you start narrow edge at xt.
Yes.
And then
look at the height at ys.
At ys. Okay.
And you do it all together for all xt with the same noise.
Okay. But this is the KBC universality class, and there are other universality classes like the Edward Wilkinson universality class, where the scaling exponents are different, 1, 2, and 4. This is related to the additive stochastic heat equation, and also another recent development by Heider and Cannizzaro from a few years ago, that which is basically a Brownian motion defined on the Brownian web. I will define the Brownian web later, and the scaling exponents here are 1, 1, and 2. I'm telling you all this because our objects will be actually in a new universality class, which is different from the KPZ and different from these two as well. So let's see how we can define these objects. Well, I start with the random walk web distance. And the random walk web distance is defined on the even integer lattice, where at every point in the lattice, you can either have an arrow up or down. So this is a direct in the lattice, in the sense that every edge should point to the right. And at every point, you flip a coin, which is an IID choice for every place that your arrow will point up or down. Given this environment, you say that you will define a graph which has one outgoing edge from every point, and then you say that you can travel along these directed edges for free. Okay, so I can define more formally the edge weights to be equal to 0 if you travel along these trajectories, and it is 1 if you traverse an edge where you don't see an arrow. So like here. Okay. So once again, there is this lattice, which is the even integer lattice. You are always only allowed to go to the right, and still, as much as you can, you will use these black edges, what are remained, which are actually the trajectories of coalescing random walks to the right. But if you cannot, then you are allowed to use other edges. But if you use other edges, then you have to pay a price of 1 unit. The model here. And what you compute is that for each pair of points, so like IN and JM are on the lattice, what is the minimal number of jumps that you have to make if you want to go from one point to another? Okay, so that's the random band distance between those points. And so you can see on the picture that there are these two purple points, and on the left and to the right, and we would like to get from one to the other. And you see that there is a trajectory which has these three places where edges with weight 1 are used. So from this you see that the minimal number of jump is at most 3. Maybe it's not so obvious to prove that that this is actually equal to 3, but I can convince you if we start drawing these regions with different colors. What are these regions? I will tell you that we fix this target position, this purple dot on the right. And first of all, I would like to identify those points from which this purple target point, this one, can be reached with cost 0. This is going to be the tree corresponding to that vertex, namely those points from which there is a random walk trajectory. And the boundary of this is going to consist of, it will consist of 2 curves, and these 2 curves are going to be in the dual lattice, and in the dual lattice, these 2 blue trajectories coalesce at some place here and down here, and then they coalesce, this form what is in between and adds distance 1 to that bright purple point. And very similarly, you can think about those points from which you have to jump once to reach to the purple point. And if you identify those, it can be described also in terms of backward dual paths. And similarly, you can build up these regions for different integer numbers. And therefore, if you see that the starting point is not in the cluster of distance 2, then you can be sure that actually in this example the distance must be equal to 3. I just wanted to point out that these regions, that identifying these regions is very useful to understand and describe the distance. What is our aim? We would like to study distance function between faraway points, and we would like to see the scaling limit of it. And if these were constructed by coalescing random walks, you will not be very much surprised if you would see the coalescing Brownian motions in the limit, and this is indeed the case. So the limiting object is related to the Brownian motions that are coalescing. And the coalescing Brownian motion, the system of coalescing Brownian motions is called the Brownian web. And the Brownian web has the following history. It was already invented in the PhD of Aratia, which or some manuscript of Aratia, but later in the paper of Balint and Bernoulli-Exponential, it was constructed for the scaling limit of some special random walks, and it was called the true self-repelling motion. And the scaling limit was of these random walks was called the true self-repelling motion. And the Brownian web was used as the local time of this special random walk. And later, 20 years ago, the topology and the name of Brownian web was given in this paper. What is it about? So you can imagine that if you have finitely many points on the plane, then you can start coalescing Brownian motions running to the right, and you can sample it very easily. Still, if you have countably infinitely many of them, then the construction is quite straightforward. The question is how to extend this to all points of the plane. Actually, in parallel to constructing this object, we can also think about backward Brownian motions, which is shown in the picture down. What you see is that from the blue dots, I take finitely many blue dots, and from the blue dots, I start coalescing Brownian motions to the right. And from the right, from the red dots, I start another coalescing family of Brownian motions, all going to the left, with the condition that these two sets of Brownian motion do not cross each other. They can intersect, but they never cross. And it was proved by Balint and Werner that you can construct this object in the following way. You take the starting points one by one, either the blue ones or the red ones, it doesn't matter, and you sample Brownian motions. The blue Brownian motions go to the right, the red Brownian motions go to the left, and given finitely many of those coalescing paths, the new path will coalesce with the Brownian motion of the same color, and it is reflected in the Skorokhod sense from the opposite color. And it is a theorem that the distribution doesn't depend on the order which you take, and you can extend this picture to the Brownian web and its dual, which consists of the Brownian motions going to the left. Okay. Already in that paper, which I was referring, there was a description of the special points. You can convince yourself easily that that there should be points. If you want to start Brownian motions from every point on the plane, you will have certain points which will have multiple outgoing or incoming paths. And if you denote by M in and M out the number of incoming and outgoing paths in a point, actually you have to be a little bit more precise. Equivalent sequences of incoming and outgoing paths. And then there are six possible types that can occur. And the typical points in R2 are 0, 1, meaning that there are no incoming and one outgoing paths. But there are also other types. And for our construction, the 1, 2 points play a special role, and they will be important, which I try to show on this figure. So there is a blue trajectory going to the right, and then this exactly at this position, it keeps on going, but there is another path emanating from the middle point, and in the same time in the dual, there is an incoming dual path, backward path, and it also has two outgoing dual paths. Yes, and at these so-called 1, 2 points, there is always one outgoing path in the Brownian web, but also there is another additional path. So how do we define the Brownian web distance? Well, the idea is the following. It is very similar to the random walk web distance, where we allow to travel on the trajectory for free, namely that we allow to use the Brownian web trajectories without paying any price. We pay 1 unit of price if we switch between two Brownian web trajectories. What does this mean? It means that if we arrive to a 1, 2 point, then, okay, let me go back and show you that in this picture, there is this blue path which we are following, suppose, and then if we just continue this path, in this picture, the lower path is the continuation of the one that goes into the point, and that special 1, 2 point. But if we switch, and instead of using the lower blue path, starting from the middle point, and we use the upper one, then we have to pay a price of 1 unit. Okay. So in other words, the Brownian web distance between 2 points on the plane, Tx and Sy, is the minimal number of such jumps at 1, 2 points. Okay. This defines an integer valued distance function on the pair of points on the plane. It is very, very non-symmetric because the role of the 2 points is different. For example, the target point, it has to be such a point which has an incoming path. So that's why this last property is true, that the Brownian web distance is equal to infinity for a typical path xy, where this sy is the second variable. So if the second variable, the second point, is not such that it is hit by a Brownian web path, then automatically the distance is infinite. But in Tx, you don't see this very, very strong irregularity. So it is non-symmetric. It's distance from point to itself is defined to be 0. It satisfies the triangle inequality, and it also has a lower semi-continuous version. I will not very precisely tell you what it is. It only differs at special points from the Brownian web distance that I told you. In some of our theorems, the Brownian web distance is in other ones, the lower semi-continuous version you can see in the results.
So this is a stupid question, but it's something you said that you always like to use the lower path for 3, but then okay, 1, 2, jump to
yeah, this is just on this example, because so there are two, actually, the 1, 2 points can look like this, as in this picture, that you start so here in the middle point, there is an incoming path, and you can continue it for free. So namely, that in the Brownian web, the Brownian motion that comes in is continued to the right. And in some of the 1, 2 points, the additional path that goes out from this point goes above, and in some other points, which look different, the additional path goes down compared to the continuation of.
That you can check by looking at the dual and see which way they.
Yeah, exactly. So
okay.
if at this point,
Yeah.
in the dual there is something which is hitting from above,
Yeah.
it's different from if it's hit from the below.
Yeah.
So these are the 2 types. And actually by symmetry both. Okay, so these are the places where you can switch. Okay. And immediately from the Brownian scaling, the scaling variance under the Brownian scaling of the Brownian web, it follows that the distance that we can define in this way is scale invariant. So if you see in T and X, we apply the Brownian scaling, then the distribution of the distance is the same. This means that the scaling exponents of this new object is 0, 1, and 2. So this is scaling invariant with these exponents, which are different from the universality classes we have seen so far. And there is a convergence theorem, which is saying that if you start with the random walk web distance and rescale it according to the 0, 1, 2 scaling, then it will converge, actually in this case, to the lower semi-continuous version of the Brownian web distance. And it happens with probability 1 in a very strong sense in the epigraph topology. And actually this lower semi-continuous version is of course lower semi-continuous. Okay, so that's the convergence result that we could prove. And here comes the relation to the KPC universality class. Of course, the object is scale invariant under 0, 1, 2, under the 0, 1, 2 scaling, so we cannot have a scaling limit in the usual sense. But if we take a shear transformation, namely that, okay, what is here? So this is the Brownian web distance, and the target is 0 and r minus, meaning that the semi-infinite vertical half-life. So let me try to go through a picture. Is that here is 0, 0. So we want to hit this semi-infinite line, and we go in that direction. So m is the parameter that goes to infinity, and for simplicity, you can just take t equals 1 and z equals 0. And then the statement will be a little bit simpler. So you go in this direction and you go very far away, then you will see KPZ scale. If you play with this theorem a little bit and apply the 0, 1, 2 scaling, you can change this Tm and 2Tm to something that has a different slope. Okay, so it's not very hard to get KPZ scaling in any direction that is different from the horizontal one, and actually you will recover the area. This is for t equals 1. This is the area process. And this is the directed landscape when you take 0, 0 in the first coordinate. A very similar result holds for the random walk web distance. You can take the corresponding half-line as a target, and if you look at in any direction, my eta is something between 0 and 1. Oops, I'm sorry. It's between 0 and 1. If I look at any direction, then there is still a convergence to the direct landscape. I mean, yeah, so this theorem is all only stated here for simplicity for t equals 1.
And it's in as processes in 17.
Yeah.
Convergence in distribution or what it was?
Yeah, it's
Yeah.
processes of
Processes.
And what if you start from some other points back there and do it in the 4 parameters?
What do you the other?
No. Can you do it if 0, 0 were called x and x, and I shift back there by.
Yeah, this was a conjecture that was actually recently solved by the paper done at the so yeah, I haven't put it in the slides, but there is a conjecture that there is convergence also in the other 2 variables, but that so that the symmetry is or this behavior in the other variables. Yeah, that's a good question. And also we could, so if you look at the second statement here on this slide, and there is an expression for C1, the constant in front of the leading order of the random walk web distance under the scaling, then you can get the formula for the shape of disc or balls of growing radii, and this is depicted in that picture. As I said before, these theorems apply in the case when the slope at which you are looking is different from horizontal. And we also studied the case when we go very far away in the random walk web distance, but the direction is horizontal. So here we start from the origin and we go n to the right, but it's horizontal. Then the scaling is logarithmic in n. Okay, so we can prove this result that we probability 1, this ratio will be. So let me a bit talk about another model, which is a variant of the random walk web distance. It is called the Bernoulli-Exponential first message percolation. The lattice is the same. So you have the trajectories of coalescing random walks going to the right. Those can be used for free. And for all other edges in the lattice, which you don't see here on the picture, there I put independent exponential one random variables. And the question is the same, but we denote this by t now. T is the minimal total weight of paths between the point IN and JN. And we can ask this question that using only paths going to the right, what is the minimal number of weight? And you would like to describe that. Also, we allow for writing an interval in the last coordinate in this distance. And why this model is useful is because there are actually explicit formulas, explicit flat-bond determinant formulas for the distribution of these quantities. It was also shown in the same paper that if you rescale in a way that kappa is positive, so you are away from. So what is the picture? The picture is that now you start from the origin and you go far away. So this is n, and if you let kappa to be positive, then your height is kappa n, roughly, and you are asking what is the minimal length from the origin to this half line. And it turns out that under the right scaling, it converges to the traceability distribution. In a later paper, these people, Theon Barakan and Lichnowsky, could improve the result and go closer to the vertical line, but still they were away like n to the 2/3. The traceability distribution remains here. But the most interesting question could be that what happens if you go square root of n close to the vertical line? Because notice that if you start, so if I go back to the model, then obviously started from the origin, there is a random walk trajectory which goes to the right. At distance n, it fluctuates at square root of n. So certainly you will see somewhere this path with zero weight. So that's why the question is interesting. And actually the result is the following, is that if you rescale diffusively, then I mean in this way that n and square root of n inside, and then you have to magnify your distance by square root of n, then it converges to in distribution to a new random variable, which is given explicitly in the following way. It can be equal to 0. This corresponds to the free path, which after rescaling converges to a Brownian motion. The probability for this Brownian motion hitting something about h times square root of n is obviously equal to that Tail probability of the normal. And the probability that is bigger than s can be given as a flat-bond determinant of a certain kernel. Okay, And it is actually this H is going to be an interpolation between the Gaussian distribution and the Tracy-Widom distribution. But to see that, it's better to consider the height function. The corresponding height function in this case is going to be defined like for a given end and threshold R is the maximum of those positions where your distance is smaller than or equal than R. So basically, you follow some trajectory where you have distance at most R, the highest position at which you have this, and under the scaling, which you see here, like n, and the threshold should be proportional to 1 over square root of n. Then this position, this H is telling you the position of this height function. It is also equal to square root of n, so you divide it by square root of n. This converges to a random variable whose distribution is expressed in terms of the same Fredholm determinant. And this Fredholm determinant has the property that for s equals 0, so if you are looking at so s, that s is equal to the R above here, so you are actually looking at the position of this Brownian motion. Then, not very surprisingly, you recover the Gaussian distribution, and it's also so although this theorem is only true for s positive, with the formal substitution, you will get back the Gaussian distribution also from the kernel. And if you let s go to infinity, then this crossover distribution converges to the trace. Okay, and I think depending on how much time I have, I go back to the original model and I tell you some ideas about the proof, unless you have any questions.
Just the last thing is just proved by from explicit one.
Yeah, this is all depending on. So I showed you that Barakan
It's the top formula.
Yeah. So this was obtained in the 2017 paper, very explicit for the Fredholm determinant, and after some manipulations, we could prove.
And it's not one of the already known crossovers.
No, we haven't seen this. So it is very explicit. It looks. I don't really know how to. So it is somehow reminiscent to this Pearce things, but not really, because somehow the role of the variables is not the same. So it's 1 over u and 1 over v is special.
Yes, so it's the variable, like the s or h switched in the determinant. Like the probability th greater than s. The space is on L to h infinity.
Yeah, it's on h infinity.
It's not s.
Not s, yeah.
Oh, okay.
So there are two variables, h and s. So in this case, h is telling you how much you go up on the scale of square root of n, and s is here the level at which you are looking at the probability. So these are two different variables, and if you do the transformation and you go to express, actually this is the same theorem as before, just expressed in terms of the height function, then actually the position of the two variables is switched. Is the same trick as in data also. If you think about height function of particle position, that's the same. Okay. So some ideas about the proof. So let me think about. Let me recall. I think it's better to go back to the theorem what I would like to talk about. So I'm now trying to tell you some ideas about this convergence theorem, and that the random walk web distance converges to the Brownian web distance. The encoding of random walk web distance and Brownian web distance is possible through the regions which are telling us. So we take we take a target position here, and we describe the set of those points from which this target position can be reached with 0 jump, with 1 jump, 2 jumps, and so on. You can do this for the random walk-up distance, and also for a special point where there is an incoming, where you condition that there is an incoming path, you can ask which are the points that can be reached with 0 jump in the Brownian web distance, with 1 jump in the Brownian web distance, and so on. And this is an equivalent description of the distance function. And what we actually do is that we prove the convergence of the curves, what you see on the top, that are in the Brownian, that are in the random walk web distance, to the boundary curves of the random walk web distance. Which seems quite clear for the first curves, for example, if you believe that this first curve is nothing else but the random walk starting from this position and another random walk starting from that position, run until they first hit. Then you see 2 Brownian motions running until collision. So it's not very surprising that first object will converge to the second one after diffusive scaling. But for the remaining ones, we have to understand what is the relation between neighboring curves. So the first 0th curve, first curve, second curve have to be given inductively. And it turns out that the distribution of the curve RK, which is the boundary curve in the random walk web distance, can be given as the discrete scorable reflection of the previous curve. And for the Brownian web distance, it is the scorable reflection of the Brownian motion on the top of the other Brownian motion. And here, this is maybe a more technical slide, so where is the proof how this convergence in distribution can be turned into an almost sure convergence. So I think I will skip this, but why is it interesting, or what is very interesting, I think, is that how you recover the relation to the KPZ universality. As I mentioned, you recover Brownian motions that are reflected on the top of each other, and it is very closely related to the Brownian last passage percolation. So what is the Brownian last passage percolation? You take a time t and an n to be an integer, and you take independent standard Brownian motions W0, 1, 2, and 3, and so on. And a partition, you take the supremum, the Brownian last passage percolation value LTN is the supremum over all subdivisions of the interval 0t, and on the interval 0t, over this subdivision, you take the increment of the first Brownian motion, then the increment of the second Brownian motion in the second interval, and so on. You take the supremum of all of those, and this is the Brownian last passage percolation. If you rewrite this definition by induction, you can see that this LTN satisfies that it is just a scorable reflection of a Brownian motion on LP with an index n minus, with index n minus. So if you want to ask yourself, this rho is the boundary curve with this particular index, which you can think, you can forget about this z, you can think that this is being equal to 0. And so a boundary curve with a high index, then you can describe this in distribution as a last passage value, and the last passage value will actually have KPZ fluctuations. And this is where the KPZ fluctuations come in the picture. So in other words, you will recover, reflect Brownian motions on each other in this picture, and therefore this is the way that the KPZ universality comes. How much? I have one more slide.
Yeah, 4 minutes.
This is about the horizontal direction. Remember, what I wanted to prove is that, okay, I come back to the theorem. I just want to show the lower bound in this theorem, where I'm saying that for the random walk web distance in the horizontal direction, the scaling is the logarithm of n, and this is because of the following trick. We are considering that. Okay. So now I shift everything so that the target is 0, 0, and I'm interested in these boundary curves. Okay, so this is the target position, still the random walk web distance, and the evolution rule of these boundary curves is score over the discrete score over reflection. So the next curve would be just the score over reflection of another other random walk trajectory on the top of this, and another random walk reflected of down from the lower curve. And we do the following approximation. We say that we take a random variable ek for the ks curve, and we take a rectangle of size ek in the horizontal direction, and actually twice square root of ek the vertical direction, and so that this rectangle includes the lower and the upper boundary curve. Okay. To produce the next boundary curve, what we would need is to score over reflect a random walk on the top of this curve and on the bottom of that curve. Instead, what we do is that we score over reflect on the top of this rectangle, and similarly on the bottom of the rectangle, and then wait until they hit each other. And then the next random variable ek plus 1 will be the rectangle that includes everything what you see here. Okay? It certainly gives you an upper bound on the how far you get with the next boundary curve. And if you get with an upper bound on this, how much you can increase in this way, then you get a lower bound on the number of iterations that you need to reach position n. Okay, and I think that's it. I can stop.
Okay,